All right. So are you guys able to log into Canvas now, and see the content? Okay, excellent, very good. Sorry about that little snafu. Lecture. I cannot get rid of these items. Some of the items that are useless to me. I cannot get rid of it. Or at least I haven't figured out how to do it. Right. So are there any questions, comments, feedback from the last discussion? Yep.
I just want to make sure that I absorb what I need to from it. And so essentially just like one is high voltage and 0 is low voltage, and then depending on the transistor, 0 can be on or off, and then there's the NAND.
Yeah, a transistor can be on or off.
Yeah.
And when the transistor is on, it is allowing flow because a transistor is a valve. So when it's on, you're allowing flow through, and when it's off, you're cutting off, you're disconnecting the two ends.
Yeah.
Yep. Okay, so for the most part, that's what we talked about, but the significance of the lecture on Monday is, we can now relate transistors, which you can buy, you can solder those things onto a circuit board, they're physical. We are now relating transistors, the N-channel transistors and the P-channel transistors to logic gates, right? Because that's what we did in the lab session on Monday. The first thing I did was to implement a NAND gate, which is in the notes. And then using a NAND gate, I made a NOT gate, I made an AND gate, and I made an OR gate, right? So are there any questions about that part? Because, to me, it is kind of fascinating, okay? Because we are now connecting physical devices to things that you can do in logic: conjunction, disjunction, and negation. Is that okay? We are going from physical quantities, physical devices, to logical operations and logical values. That is the significance of the previous class. Is that okay? Any questions about that part? Because I think it is important to understand why a particular lecture is important. The details are important too. Okay, how did we make that NAND 2 gate out of transistors? Kind of important. Okay, how did we make a NOT gate out of a NAND gate? Kind of important. Those are the hows, the details. But the question of why is that particular topic was important is kind of useful too, because you have to understand what we are connecting. The stuff in between is useful, but what are the endpoints of the previous class? Physical devices, physical states. Now we have logical operations and logical values. Okay, so we're going to continue on with that topic today, and just kind of continue to move on. And let's see where we are at last time. Lots of pictures, right? So we talked about all of these pictures already, when you have 0, 0 as input. So with these pictures, when you see a thick, big arrow going down, this is flow. Okay, these two valves are turned on and therefore allowing flow in this particular direction. Okay, so it's the stuff that we have explained already. So there's no new content with these specific pictures. So with this one, we have 1, 1 as input. But with 1, 1 as input, Q1 and Q2 are turned off, and therefore you don't see any flow here. But since Q3 and Q4 are both on, then you see there's one connection here and one connection here, and as a result, the output pin is now connected to the ground, and it will experience a low voltage or 0 volts. Okay, so all of this stuff here is just explaining the same thing that I have explained on Monday already. I just did not use these pictures on Monday. We talked about this already, basically saying how we are going from transistors to logic gates, and what we have here is a NAND gate. We talked about how we can implement a NOT out of a NAND, we can implement an AND out of two NANDs, and how we can implement an OR out of 3 NANDs. well, it takes a little bit of scrolling because it's a little bit long. Is that part okay so far? Because we talked about all of this stuff here in lecture, and then in the lab on Monday, I actually used Logisim and implemented all of this stuff here. So are there any questions before we move on? Because it's good to clear all the concepts that has been talked about already before introducing new concepts. No questions? All right. So if there are no questions, we are going to move on to the next topic, which doesn't seem to be very important. It starts with numbers and values. Okay. So this module doesn't really go too deeply into what numbers are and what values are, but they are different. Numbers are representations of values. Okay? So when I say how many fingers, what is going through your mind right now is a value. Okay? I'm not going to use any words to describe it because that's going to defeat the whole purpose. Okay? So when I say how many fingers, and in your head, in your mind, you have a concept popping up. Okay? That is a value. When I ask you and say, how many fingers, and you answer, go ahead. 4. 4, that's a number. What is in your mind, the concept, is a value. When you need to communicate with me to tell me the answer, that is a number. In other words, numbers are used for communication purposes. Value is the concept that is both here and also in your head. Is that okay? The other thing is, okay, don't answer this question yet, okay? But I'm going to ask you a question, and then it will basically help illustrate the difference between a value and a number. Who am I? Okay, keep the answer to yourself, okay? So the concept of this person is a value. But when you say, oh, you attack, that is a name, which is a number. Is that okay? So the most important part is there are different ways to represent the same value. This is 4 in English. Does anyone here speak any language other than English? Go ahead. Yeah.
Deutsch, ein bisschen.
Okay.
Nummer 4.
Okay. So in German, it's that particular word. How about Spanish? Does anyone speak Spanish? Go ahead.
4.
Okay. How about Vietnamese? Any Vietnamese speakers? No?
Japanese.
Japanese, go ahead.
Yon. Well, actually, yon or she.
Okay. Chinese, Mandarin?
Say.
Okay, that's Cantonese, very good. But you can see how the same concept is now, we can give it different names. We can label it differently. And it depends on who we are communicating with, right? If you're communicating with someone who only understands, Cantonese, then you have to use the Cantonese word for this concept. Is that making any sense? So I'm making a differentiation between the concept of a number, which is for communication purposes, for writing down, for printing out and stuff like that, versus the value, which is a concept, which is physical as well as something that is in your mind. It's an understanding of that particular thing. All right, so we are done with this particular module 0281, and now we are moving on to values, numbers, and bases. We are going to talk about base conversion and cool stuff like that. Right. So the first question is, what is a number? We just talked about it. It is just a representation so that you can communicate the concept with other people. Okay, counting and so on. You can skip all this part here. I'm just using an example of how people in the past use pebbles, shells, and other objects to represent things. So that when you're trying to trade with somebody else, you don't have to bring all the grain, and the other person has to bring all the animals. You can just bring tokens representing those things. So what we'll talk about here is we are dealing with for the most part, values that we use what we call a common base multiple digit representation. It's really just a fancy name of saying okay, this is how we do things normally. So without looking at all of these things, let's take a look at this example here. Okay, I'm skipping all the other stuff you can read about it. I'm looking at this particular number, 16.375. Unless I tell you this is not a decimal number, you can assume the default is decimal. Okay, so I'm breaking it up into its components. It is 10 plus 6 plus 0.3 plus 0.07 plus 0.005. Does anyone have any questions or thing to say about the first line of this particular equation? No questions, right? I mean, if you ask any middle schooler, they can tell you that, oh yeah, what is the significance of this? Then you look at the second line. The second line says, oh, by the way, we can write 10 as 1 times 10 to the power of 1. We can write 6 as 6 times 10 to the power of 0. We can write 0.3 as 3 times 10 to the power of -1, and so on. Okay, cool. Any middle schooler can tell you that, yeah, I understand that part too. What is the significance? The significance is we're using one single base 10. Do you see how this 1, which is coming from here, is representing the quantities of 10 to the power of 1, a power of 10. This 6 here, which is coming from this 6, is representing how many 10 to the power of zeros do we have in this number. What about this 3 here? This 3, which is also this 3, is specifying the quantities of 10 to the power of -1. In other words, when you look at the individual digits of a number in any base, it is telling you the quantity of a particular power of that base. And that's why I call it common base multi-digit numbers, which is just a really super fancy and stupid in a way name for how we represent values today. Is that okay? But you have dealt with far more complicated and archaic systems of representing values, and you don't even realize it. Okay? Let's go to a particular example. I'm going to use this as an example to illustrate why base conversion should be really easy. It's a very easy concept to understand because you have done something that is far more difficult than base conversion already. Okay, so let's say you are working for McDonald's or some fast food place, and somebody gives you a $100 bill for buying a hamburger. You have to figure out the change, right? Let's say the machine is broken, so you have to kind of do the calculations. Well, okay, the machine tells you the exact number as change, but you have to figure out what kind of bills and coins to use to make up for that amount. Is that okay? So let's say the amount that we have to deal with, since it's a single hamburger, so let's say your change is going to be $92.87. This is the change. So my challenge to you guys is, do you know how to use the least number of bills and coins, assuming that you're only using the common ones, to give the customer back this much money? Then you know base conversion already, because the currency system that we use in the United States is really difficult to deal with. Difficult to deal with. I know how to do this. How can you say this is difficult to deal with? It is difficult to deal with. So if you look at the bills and coins, in a currency system, where do we start? The smallest amount.
1 cent.
1 cent, a penny. Okay. The next one up.
5.
A dime.
Nickel.
A nickel, right? The next one is a dime. Sorry. And then where? A quarter. Now we do have half dollars, but they are not common, so I'm not going to use those. And then we move up to $1, and then what? 5. We do have $2 bills, but once again, they are not common.
Did they get discontinued?
No, you can like.
No, there's
put
still discontinued.
Huh? Sorry? Okay, so we have $10 bills, and then we have $20 bills, and then we have $50 bills, and then $100 bills, and so on, right? So then you look at the multiplication factor between all of these things. From between a penny and a nickel is a multiplier of 5. Between these two is a 2. Between these two is 2.5. Between these two it is a 4. So far, there's nothing repeating. There's nothing repeating here. And then we have a 5 again. So we will say, oh, maybe it's just cyclical. The next one is a 2. Yeah, see, so it seems. And then the next one is a 2, which is not a 2.5, right? And then you get a 2.5. There is no regularity to this particular system. It is not a common base. And yet you feel comfortable, right? You know, does anyone not feel comfortable working at McDonald's because you have to figure out the change using the least number of bills and coins?
Not for that reason.
Most people, you can drag someone off the street and most people would not have a problem. So you guys can do base conversion already. Because it's actually easier. Okay, base conversion is even easier than dealing with this stuff here. Okay, so let's cross this out, and then we'll use an example. Okay, so let's say some weird country decides that base 10 is not the way to go. We'll use base 2. Okay, and throughout this class, you will see why base 2 is a much better base to use for many different purposes. Okay, but let's just say that this new country decides, oh, we're not going to do base 10, we'll do base 2. Okay, so when you have a country that is doing base 2, everything will be in base 2. Okay, so they would use a base of 2 instead of the base of 10. So in terms of money, they're going to start with, I'm going to pick a particular number here. So they will start with $1/8 of a dollar. Okay, that's the smallest amount you can specify in that particular country. $1/8 of a dollar. Next one up is a quarter. Next one up is a $half. Next one up is a dollar. Then you have $2 bills, $4 bills, $8 bills, $16 bills, $32 bills, $64 bills, and so on. Is that okay so far? You know, we are just making up a new currency system where there are coins representing $1/8, a quarter, and a $half, and then we have bills that are of the values 1, 2, 4, 8, 16, 32, and 64, and so on. Okay, next one is 128, 256, 512, 1024, and so on. Okay. So now I want to specify a particular change. The number that I have chosen before is not going to work well with this system, so I'm going to make another one, which is $92 and this amount, which is basically 5/8 of a dollar. Is that okay? No, this is actually 7/8 of a dollar. Okay, so now I ask you, okay, I want to use the least number of coins and bills in order to have this amount of money specified. How do you do it?
Greatest to least. Greatest to least.
From the greatest to the least. Okay, very good. Okay, so so let's say I have this list continuing with 128 and so on. Okay, so what do you do? You compare $92.875 to 128 and go like, we don't need that. It's too much, right? So the next one down is going to be a 64. $92 has at least 164. Cool. So you say, okay, we'll specify $164 bills. Okay, and then your remaining becomes what? I'm really bad with arithmetic, so you guys can do the math with me.
28
Okay, so 28.875 is what is left, right? So you look at $28 and $28.875 and go like, okay, so let's try 32. 32 is too much. And then you go to 16 and go like, oh, okay, we know there's 116 in this amount. So you say, okay, we need one $16 bill. Is that working so far? I mean, are you guys following along with the logic? Okay, cool. So you subtract 16 from 28 point something, and even I can do this one. I hate base 10, it's so hard to use. Okay. Okay, so now you have $12.875 left. So you try 16 already. Now the best part of binary numbers is you don't have to retry 16. Once you have used it, you don't have to consider it again. So the next one down is 8. There's one 8 in 12 point something, so we'll specify one of those. So now we got $4.875 left. You look at this number, the next one down is a 4. We'll take one 4. So one $4 bill. This is an $8 bill. And then you have $0.875 left. And then you go down to a $0.50, right? Technically, you have to go to a $2 bill first. Go like, no, this is less than 2. Then you go to a dollar coin. You go like, no, this is less than $1. So that's why you can skip those, quote unquote, skip those until you get to a $0.50. So you say, oh, we need one $0.50. And after that, you get 0.375 is left. You look at this number and you go like, we can use a quarter. Then you have $1.25 left. And you say, we'll also need $1/8 in this case. And then you have nothing left, which means you're done. Are we doing okay so far? Okay. But you just converted a decimal number into a binary number. What binary number? I don't see a binary number here. Okay, let's fill in the gaps here, okay? So there are gaps here that makes this not look like a binary number. So we'll go ahead and fill in the gaps. So we have one $64 bills, but what I didn't say here is we have 0 $32 bills. Okay. So it's pretty easy. 16 goes to 8, 8 goes to 4. 4 doesn't go half, immediately. So I'm missing a $2 bill. I'm missing a $1 bill, right? Now I have a binary number. What binary number? I still don't see a binary number. Okay, so let's try to specify the amount of each bill and coin, but do it horizontally. Or if you prefer, you can look at this way. Then you have a binary number. Okay, so we'll go ahead and see if we can do it in a slightly different way. Let me see. Let me see if I can do this. Have two windows so that one, yep, there we go. That's cool. So I can have one staying with what we just worked with, and then the other one to actually collect all the numbers. So we have 164, 032, 116, 18, right? We got 14, we got 02, 01, and I'm going to use a dot here, and then we have 1/2, 1/4, and 1/8. That's your binary number. Not only is it a binary number, it is a binary number that has a fraction. I wouldn't call this a decimal point. I would call this a binary point. Because a decimal point, decimal means base 10, so this is a binary point. Whoa, okay, hold on a second here. Is this really representing the same value that we started off with? Well, let's convert the binary number back into base 10 and see if they match, okay? Because if they don't match, then we have a problem. But Tech, you never said anything about reading, how to read this number. It's a base 2 number, so if I use parentheses 2 after a number, it means you have to look at it as a binary number. In documents, I use a subscript of 2, but since I cannot subscript in a regular text editor, I just put 2 in parentheses. Okay, so let's look at this number, and from here on, they're all binary until I say they're not binary. Can we look at this number as something like this? Even though it's a binary number, can we still use this method? And why can we still use this method even though it's not a base 10 number? Yep.
Because it's still a positional number system.
Yep, because each column cannot add up to anything that will require another, there won't be any carry. Okay, so this would be a good time to check that I'm actually streaming. Yep, I am streaming. It's capturing the mic. All right. And if you want to, you can always put extra point zeros in all of these cases. Not required, but doesn't hurt. Okay. Can anyone say that, oh, this doesn't follow? This makes no sense. Well, it doesn't make any sense in the way that it's really tedious. Why would you want to break a number down like that, right? But any other questions about how I can break this number down and say, oh, you know what, that binary number is really the summation of all of these components. Should not be a big problem. So now the question now is, what is this? What is the value represented by this binary number? By counting the number of zeros, you can kind of tell that it's telling you the quantity of a particular power of 2. So the question is, we have one of which power of 2? Well, let's do some counting here. This is the least significant digit before the binary point. It is always telling you how many ones we have, which is 2 to the power of 0. So 2 to the power of 0, 2 to the power of 1, 2, 3, 4, 5, 6. In other words, this is telling me that we have 1 of 2 to the power of 6. Is that okay? This is a pretty important transition. This is telling me that we have 1 times 2 to the power of 6 because of this part here. So this would be a good time to ask questions. Any questions about this part? By counting the number of zeros to the right-hand side of the 1 until we get to the binary point, I know that it is representing, oh, we got 1 of 2 to the power of this number. Is this kind of analogous to the first example in base 10? Yep, except now we're using base 2. So we are raising the power of 2 to the number of zeros to the right-hand side of that digit. Cool. So that means I can now rewrite this as 0 times 2 to the power of 5 plus 1 times 2 to the power of 4 plus 1 times 2 to the power of 3 plus 1 times 2 to the power of 2. Okay, and then I'm going to skip the 0, because it just doesn't need to be represented here. Okay, so what about this guy here? It is representing the quantity of another power of 2, but it is on the right-hand side of the binary point. What does that mean? When you think about the base 10 case, what is that telling you? A negative power. Very good. Okay, so this is 2 to the power of -1. So that's, oops, wrong place. There we go. So we have 1 times 2 to the power of -1. So the -1 comes from that 1, this 1, being on the right-hand side of the binary point. So we are dealing with fractions now. But you can see the general equation is still pretty much the same. We are just looking at each one and say that, oh, we got 1 of this power of 2, and then we got 1 of those power of 2, and so on. Is that okay? So when you add up these numbers, 2 to the power of 6 is 64, 2 to the power of 5 is 32, 2 to the power of 4, okay, I think I might be missing, nope. There's no 32, sorry, because it's a 0 as a multiplier. So the next one up is 2 to the power of 4, which is 16. And then the next one is an 8. The next one is a 4. Next one is a 0.5, 0.25, 0.125. There we go. And let's see, does it add up to the value that I want? Yep. So there you go. So now I have just demonstrated how to convert from base 10 to base 2, and then from base 2 back to base 10. Is that okay? Excellent. So the example that I have just used is not really in the notes, but it's a much more interactive way to kind of demonstrate how it works. In the notes, it's a little bit more dry. Okay, it is just using a summation symbol to represent, oh, if you have a common base multi-digit number where D0 represents the rightmost or the least significant digit, D1 represents the second least significant digit, and so on, and then D-1 represents the first digit to the right-hand side of the decimal point, then you have this equation here. The value that is represented by all of these digits is a summation where I goes from theoretically negative infinity as an integer to positive infinity as an integer, d subscript I, which is representing which digit we are talking about, times 10 to the power of I being the position of that digit. When you're dealing with base 2, the only change is you're changing the 10 to a 2. So in general, if you are using base B, that's the equation. B is the base. In other words, if you want to, you can have a system that is base 7. It's a prime number, it's kind of odd, but it can work. Let's use that as an example, because whenever I see people frowning and go like, yeah, let's use that as an example. So let's look at 205 in base 7 and say, what is the value represented by 205 in base 7? Who would use base 7? Well, if you have a species of animal with only 7 fingers, that's the base system they're going to use. What is the meaning of digit? Finger. Exactly. So because we got 10 fingers, we like to use base 10. That's about it. Okay, so base 7. So we break this up into 200 in base 7 plus 00 in base 7. Whoops. Plus 5 in base 7. Okay, we break it up based on the digits first. So 200 in base 7 means we got 2 of the following power of 7. What power of 7 are we dealing with? By counting the number of zeros. 2 zeros, right? So we are dealing with 7 to the power of 2, to the power of 2, plus 0, so that's the middle digit, easy. 5 times 7 to the power of 0 in this case, which is just 5, okay, fancy way to say it. So this is 2 times 49, 49 plus 0 plus 5 by itself, and 2 times 49 is 98 plus 5, so this number is known as 105 to us people, 103, sorry, to people who know to use base 10. Is that okay? Is this easier than dealing with money, like bills, coins, and whatnot? It should be, but it's not, because you haven't done this, repeatedly for the past, 17 or 18 of your years of your lives. It's really a matter of, how many times you have done it, not so much the concept. Is that okay so far? Cool. All right.
How about a little base 16 now?
Huh?
How about a little hexadecimal?
We'll get to hexadecimal when we run up the limit of every number in binary is like this long.
Yeah.
Can we write it a shorter way? Yes, we can, and it's easy to convert between base 16 and base 2. But we'll get to it when we have the need to do it. So far we are just talking about, okay, how are values represented by common base multi-digit numbers. Now that is a term that only I use, so don't even mention to your professor, math professor, and go like, hey, Professor so-and-so, my computer science teacher mentioned something about common base multi-digit numbers. What is that? They won't know, because I came up with that term. All right, so the conversion goes the other way using mod operation and so on, binary numbers. Okay, so we have gone through all of this stuff already. Okay, this is just a lot of text that you are supposed to read, but when in class, I'm not going to read my own notes. I will die of my own boredom if I were to read my own notes. So conversion exercises, you can write a program to do base conversion. How would you do that? So let's say I want you to write a program to convert from base 10 to base 7. How would you write that program? The input is a base 10 number. Let's just stick with integers so you don't have to deal with your fractional parts. So I give you a base 10 number and you have to print a base 7 number that represents exactly the same value. How would you write that program?
Break it up.
Well, first of all, you have to parse the input. So you can cheat that part, because if I tell you that the input is in base 10, then cin can automatically deal with base 10 numbers. It knows how to read a base 10 number as ASCII code of the digits and convert it into an internal representation. Then you have to do the conversion to base 7 to print it back out. There was a question earlier? No? Okay. So other than that, are there any questions about base conversion, or how we interpret numbers in general? Questions? All right. If there are no questions, we're going to move on to the next slide. I'm going to keep this one up. The next slide is jumping straight into binary addition. Okay. So if you have any questions about base 2 numbers, how to do the base conversion, you might want to mention it now. Yep, go ahead.
What about negative numbers? Do
Negative numbers?
exist in binary code?
That's a very good question. So you kind of have to think about it in a different way. Okay, so remember in the previous class we talked about physical devices, physical states, right? Transistors, is it on, is it off? And then we arbitrarily say that if it's on, we'll call it a 1, if it's off, we call it a 0. Okay, we're just arbitrarily assigning meanings to physical quantities. Remember that? Okay, so I can now say that, a high voltage means true, but it can also mean a 1. Low voltage can mean false, but it can also mean a 0. But what about the negative thing? You don't actually have anything to explicitly represent the negative thing. So we'll get to it, okay? We're not quite there yet. So when we talk about 2's complement, or how we represent negative values, then we'll get into that discussion. So for now, don't worry about negative quantities, right now. Is that okay? Cool. So remember that, okay? Because we'll definitely get to negative values. All right, so we're going to talk about adding numbers. Okay, now this obviously is kind of boring because it's got a lot of text in it. So instead of using that, I'm going to give you examples, okay, in base 10. So I always start with base 10 because we know base 10 already. Well, we should, right? We should know base 10 already. What is 2 plus 3? In base 10, of course. How do you know it's 5? Okay, because for the most part you memorize all this stuff already. Okay, it is not something that you use your finger right away. Go like, oh, we got 2, 3, and then 1, 2, 3, and then this value is 1, 2, 3, 4, 5. So 2 plus 3 is 5. Okay, this is what they do in the first or the second grade, I think, in elementary school. Yeah, but at some point they memorize all of this stuff here. Okay, cool. Another example. What is 7 plus, let's make it 6, okay? Aha! So this is going to stump some first grade or second grade students. Why do you think it's going to stop some students at that level?
They can only count to 10.
Because you can only count to 10, because you only got 10 fingers, right? So you go like, okay, we got 7, so we got, 1, 2, 3, out of fingers. So they're now introduced to a 2-digit number, which is 13, right? Because you can represent the quantity and go like, oh, okay, it's 10, and then there's 3 after that. We know it's 13, right? But in this class, since you're not in 2nd grade or 3rd grade, what went through your mind when I asked you what is 7 plus 6? Why do you know it's 13 like, boop, right away? Because you got the table memorized. How many entries are in that table? Okay. Well, let's take a look. Okay, so you're talking about an addition table, not a multiplication table, right? So you have 0 to 9 in theory on one side, 0 to 9 on the other side. So let's call this x, and we call this y. And then each number is representing what is x plus y. Okay? So this table, in the current form, has 100 entries. Now, not all 100 entries are difficult to remember. Some of these are trivial because you say, oh, anything that involves zeros are pretty easy. They don't need to be memorized because 0 plus whatever or whatever plus 0 doesn't change the value. It's the same. Okay, cool. You don't have to memorize those. And then you say, addition is commutative, which means you can change the order. X plus y is the same thing as y plus x. So you say half of these entries we don't have to memorize because it's the mirror image of the other half. So now you're talking about 81, and then you divide it into half, which is about 40-something entries. Of the 40-something entries, some do not involve carrying. So you say, oh, that's fairly easy to understand, fairly easy to remember. So you shrink it even further. But you still end up with quite a few number of stuff that you have to remember. Because if you have a younger sibling or if you have a child who is currently going through addition at school, they have to practice a lot to do this accurately, to do this reliably. You and I can do it kind of quickly because we got this memorized for many, many years. But when you're learning these things, it's not something that you can learn and master in a week. This is something that will span over at least several weeks in, I guess, 2nd grade or 3rd grade. Is that making any sense? Because it involves a lot of memorization, which also means it involves a lot of practice. The teacher has to grade all of that stuff and go like, nope, 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 nope. And then the kid has to go like, okay, I guess I haven't got the table memorized yet. And they go through that and memorize even more. Is that making any sense? Okay. So the question is, what is it going to look like when we are switching to binary? In other words, all numbers can only have zeros and ones. What happens to the addition table? It gets smaller. It gets way smaller. It gets trivially small. Let's look at that. Let's look at that table. That is the entire table, unsimplified. 0, 1, 0, 1. Okay, so 0 plus 0 is a 0. 1 plus 0 is a 1. 0 plus 1 is a 1. So the only one you have to kind of think about is like, well, what about 1 plus 1? Well, 1 plus 1 is 1, 0 in binary. Okay, is that part okay? It is not 2 because the digit 2 does not exist in a binary number. The quantity, the value represented by 2 in decimal is represented by 1, 0 as a binary number. Because it is 1, it has 1 of 2 to the power of 1. Is that part okay? Then you look at this table and go like, okay, would this change the meaning of the table if I just had a 0 in all the other entries? No, leading zeros do not really change the value that is represented by the number. But I'm doing this for one reason. because I don't want to be stuck with single digit addition. I want to be able to do multi-digit addition. Okay? Which is the same reason why you remember, in base 10, when you look at 3 plus 9, you can look at this as 12. But it is more helpful to look at this as 3 plus 9 is 2 with a carry of 1. Then you have the ability to say, oh, now we can carry out multi-digit addition. Is that okay? Any questions? No? Okay. But this is really kind of interesting because if anyone goes back to an elementary school and tell the kids in the playground and say, you know what, if we switch to base 2, you are done with addition in half a day. You're going to start a revolution. the second graders will revolt. And they will elect you as their leader, their fearless leader. Society will change. Geeks will rule.
More so.
Yeah. Yeah, go ahead.
So they realize that counting the number of Fruit Loops they have is 30 digits.
But that's when you switch to hexadecimal numbers, which is also very easy to deal with because it's just a table lookup. Okay, and that table only has 16 entries instead of these crazy stuff that we are dealing with in base 10. Now, when we deal with subtraction, it's even worse because in subtraction, it's not commutative, which means you don't get to say, oh, the other half looks the same. Nope, they don't look the same. Okay, so this is kind of cool. Zeros and ones, and are there any questions about this particular table? Especially 1 plus 1 is 1, 0 in binary. No questions about that? That's all cool? Okay, so I look at this table, and then I use another table to look at this. I say x is a number, y is a number, and we are concerned with x plus y. But I'm separating the carry from the actual result of the addition. Is that okay? So I use one column to say, what is the result of x plus y? And one more column to say, is there a carry? What is the carry of x plus y? The notation is the same as what I use in the notes. So R is representing the result of the addition, which is this digit here, that's R. And the carry is the other digit, which is this one here. Is that okay? All right. So if I were to fill this out, how many rows do we have? X and Y are independent variables. Each one can be a 0 or 1. So how many rows would be the total number for this table? 4, very good. Because X can be 0, can be 1, but when X is 0, Y can be 0 or 1. When X is 1, Y can also be 0 or 1. Is that okay? Okay. So the rest is just copying from the table. From the other table, the result is the least significant digit of each cell. So we were basically saying 0 plus 0 has a result of 0. 0 plus 1 has a result of 1. 1 plus 0 has a result of 1. This one is the only one that's kind of tricky because 1 plus 1 has a result of 0, but it has a carry of 1. Is that okay? The other additions, 0 plus 0 has no carry, but I would like to say that as it has a carry of 0. 0 plus 1 is a 1, but it has a carry of 0. 1 plus 0 is 1 with a carry of 0. Are we still doing okay so far with the second table using the notation of R and C? Yep, okay. Which is just another way to look at this. Cool. So now we focus on one column at a time, and we'll focus on the one that is easy. We'll focus on the column representing the carries. If you look at this column, if you look at these two columns, you go like, I think I recognize this. Okay, I recognize this C something something as the result of some common Boolean operation. Go ahead.
I'm sorry, I was just going to ask, do you use commas instead of plus often?
I use the comma here because these two are parameters to that function. I'm looking at R as a function and C as a function. So I'm using a comma to represent, oh, the input parameters are X and Y. And here, yeah, okay. That's a good question. But getting back to this, okay, so if you just focus on these three columns, X, Y, and C of X, Y, does it remind you of a Boolean operator? The AND operator. Oh, cool. What a coincidence, right? 0 and 0 is a 0. 0 and 1 is a 0, because 0 is false, 1 is true. Okay? 1 and 0 is a 0. 1 and 1 is a 1. It matches perfectly. So that means I can define, instead of using the arithmetic definition, now I can use a Boolean definition. So we are talking about here. Okay. So we are talking about how we can use conjunction to calculate the carry of a binary addition. That is cool. What about result?
XOR?
It's exclusive OR, but if I only let you use the other common Boolean operators, you can kind of make it complicated. It will still work out. So R of xy can be defined as x not y or not xy, which is the same thing as an exclusive OR. I use exclamation point to mean negation, multiplication to mean conjunction, and addition to mean disjunction. These are, other than the exclamation point, the other ones are commonly used in computer engineering. Okay, but the bottom line is kind of important, okay, because this is a lot of details, right? So when we take a step back and go like, okay, kind of cool, but what is the big thing? Why are we studying this? What is the importance of all of this stuff? When you're dealing with binary numbers, you can use logical operators to perform the operations, to perform addition. Let me think about that sentence one more time, okay? We can use Boolean operators to perform binary number arithmetics. One deals with values, like the quantities of this versus the quantity of this, and so on. The other one is logical operation. But didn't we talk about logical operations on Monday? The AND operation, the OR operation as logic gates, and how those can boil down to NAND gates, and how NAND gates can boil down to transistors. Oh, so that means we now have a way, kind of convoluted, complex, and kind of in layers, but we have a way to use transistors to perform calculations, at least additions, with binary numbers. Is that making any sense? So, yeah, go ahead.
So is it kind of like the physical, the transistors, the
Yes.
way that they switch on and off? That's
Right.
kind of like the bridge between the values zeros and ones. That's
So the bridge has to do with, we look at 0 on the low voltage. Sometimes, okay, when you look at it logically, it is false. But when you look at it in terms of value, it is 0. When you look at a high voltage, you can say it is true when you're dealing with conjunction and disjunction, but you can also look at it as 1 when you're dealing with addition, subtraction, and that sort of thing. Okay? But since we can boil down, conjunction, the carry and also the result function into logical operators, and we know all logical operators can be done by the NAND gate, and we know NAND gates can be implemented using transistors. So now we know, oh, if you give me enough N and P transistors, I can do this. I can add at least single digits of binary numbers. That is the importance, okay? Because now we have tied in numbers and also addition to gates, to transistors, all the way down. Is that okay? All right, so the notes goes a little bit further than this. There's a lot of stuff that I skipped earlier because it's kind of boring in a way. So we go back to here, okay? Multiple digit addition. In other words, I'm teaching you guys how to add numbers that have multiple digits. Really? Well, I'm going to use the whiteboard for this because there are examples in the notes already. So I'm going to use the whiteboard to look at this. Okay, well, I'm going to use an example, not the ones that are over there already. So let's look at 592 plus 130. 37 is fine. There we go. Okay. Base 10 numbers. Can you guys do this? Are you kidding me? We are done in 2 seconds, right? Okay. But you have to go through this step by step. Okay, and then think about the whole process. 2 plus 7 is, oh, it's 9. Okay, right? It is 9, but this 9 is the R, is the result of R. Okay. Does it have any carry? It has a carry of 0. Okay, so I will be consistent and just say that. Now, in the math class, you won't do that. Okay, in any other classes, you won't do this. But in this class, I do want to do it because I want to emphasize that there is a carry. It just turns out to be 0. So what do you do with the second column? You go like, oh, it's just 9 plus 3. It is 2 with a carry. No, that is not the case. It is 9 plus 3 being 2 with a carry. And then it is 3 plus 0, which is only 3. There are 2 additions in each column. I'll say that one more time. Okay, this time, let me see if I can find a different color.
Do you
get 2.
Huh?
Do you complete the carry and then add the remainder? For 9 plus 3, you complete the 10, and then
Yes.
2 is what's left.
Okay, so let me say that one more time. The first addition involves these 2 input numbers. The numbers that are given to you that you're supposed to add. The first addition is looking at these 2 and go like, okay, 9 plus 3 is 1, 2, sorry. I hate base 10 numbers. Okay, but I don't even know this is going to be a 2. I just know that 9 plus 3 is 1, has a carry of 1 and a result of 2. So I'm going to put a little 2 here as the actual result of this part. Okay. The second addition, which I'm going to do in green, is adding the 2 and the carry from the previous column. Now I know this is a 0 and it's trivial, but the process has to be consistent. If you want the computer to do something, you have to describe a process that is consistent. Okay. 2 plus 0 turns out to be just 2. Okay, cool. That's how we end up with a 2 here. Now the third column is going to illustrate the process even more clearly. Because the first addition is the 5 and the 1. But this one here is one of the numbers that is given to you. So 5 plus 1 has a result of 6. The second addition, which I'm going to do in green, is adding the 6 and the carry from the previous digit, which now is 7. Is that okay? Now, I know most of you don't look at this and go like, wow, that is a really long way of doing this, multi-digit addition. But I need to explain it in these terms so that you can borrow the technique that you already know to binary addition. Is that okay? So is this part okay? Does everybody understand the color coding and why each column actually has 2 additions involved? Is that okay? All right. So before we move on any further, let's make this more abstract. Okay? And I will try to use the same notation that I use in my notes so that this way it will stay consistent. Okay, so we use x, y, as these 2 numbers. So I'm going to say, the first number, this is x0 is the least significant digit of x. x1 is the second least significant digit of x. x2 is the most significant digit of x. We're dealing with 3 digit plus 3 digit. Is that okay? And then we have y0, y1, y2, just like that. This is what we want to do. Is that okay? All right. So assuming that we don't have any less significant digits, this one is pretty easy. What should I write here? In terms of the R, which is the result, and C being the carry.
X and Y.
Yeah. So this one's pretty easy. It is the result of adding the digit x0 and the digit y0. Okay. But there's a hidden component here now, right? Because this addition can potentially have a carry. So this little thing here is going to be c x0 y0. It is the carry of adding x0 and y0. Okay? So using the same color coding, there are two additions. The first addition is adding x1 and y1. Okay, so that will give you a particular number here. That is going to be r x1 y1, just like that. But since you have this carry here, which means you have a second addition, I'm going to use the same color coding, which is green. So the next one is to look at these two components and add them together. So the green is going to give you a result of, well, we just copy and paste. So the first component is r x1 y1, and then the second component is c x0 y0. Close my time. There we go. And that becomes the actual result of this column. Now the trickiest part is, what about the carry to the third column? It can come from either addition. It can come from the red addition that can give you a carry of 1, but the green addition can give you a carry of 1 as well. Okay, think of this example. Okay, just hold on 1 second. This will show that case. Because 9 plus 0 is just 9. But that 9 plus the carry from the previous column will give you a carry to the next column. So let me repeat the question. The question is, what about this carry here? What about the carry that can go here? There are two ways to contribute to this carry. The first one is from the red addition. The second one is from the green addition. Which means this little bubble here is no longer very simple, because this one can be the carry of adding x1, y1. Okay, that's one source of that carry. But there's a second source of that carry, which is the green one. So this can also be the carry of adding the result of adding the red component, which is this one here, and the carry from the previous column. Yep.
Can you explain the second part again?
The second part?
Yeah.
You mean this part here?
Yeah.
Okay, so the second part is the green, is represented by the green box. So the first component of the green box is this one here, and well, I just put it in the second part, but it's symmetric, it's still okay. And then the other component is the red box here. The red box turns out to be this, and that's why it's over here. Yep.
So the only difference from the second part of the last one that you did and the bottom green one is that the green one is the result.
Yep.
And the
Yep.
top one is green.
Yep, this is the result, this is the carry. The carry you only need to, the next digit needs it. But the result is what this column needs. Yep.
When we add numbers this way, will we ever add more than 2 numbers? Like if we add 3 at one time, or is it always adding?
You're
one?
only adding 2 numbers at a time.
Okay.
That is correct.
So
This
you never
will,
get more than the carry of 1, right?
correct.
Okay.
Yep. So if you want to add multiple numbers, then you take the result of this one, and then you perform the whole thing again by looking at the third number. Combining the sum of these two, and then you add the third number. Okay? So the next one is kind of the same way. You have two additions, and then you also have to look at the carry from the previous one. So all of this stuff here, which is represented graphically, is kind of represented here using this notation. Okay, so you kind of have to relate what you see on the whiteboard, and you're more than welcome to take a picture of the whiteboard, especially after the class. So you have to relate this stuff with the notation. Well, there's descriptive sentences to describe these notations to in the notes, but that's the connection that you have to draw. You have to basically link what you see here, what you do with the generalization, and then to the notation that is in the notes. Are we still doing okay so far? I mean, I'm just giving you a map of how to connect all of these different things. Sort of? Yes? No? Yes? Okay, very good. That's the structure of this thing. Okay, so let's scroll to a particularly structural part. Okay, so when you look at this, okay, K stands for carry because I don't want you to use C. C is already used for the function itself. And S is the sum, the actual answer that you want. Q is intermediate. Okay, so when you look at this structure here, other than the first column, which is column 0, for all of the other columns where I is indicating the column number itself, it looks like it's not too difficult, right? I mean, there's a general equation to it. So now the question is, when you look at the structure of this thing here that deals with, X is the first number that you're adding, Y is the second number that you're adding, K is the carry to a particular column, and then Q is the intermediate sum, which is represented by the sum of the red portion on screen. I mean on the whiteboard, and then S is the actual sum, which is the third row, which is the actual the SI are the digits of the actual sum. Okay. So do you think this structure here, okay, without going into the details, do you think this structure is going to work in base 10? If I give you the R function that deals with base 10 addition, and give you the C function to deal with the addition of base 10 digits, would this work in base 10? Well, that's what we went through here. We went from base 10 to the generalization based on the digits. So obviously it works in base 10. Do you think it will work in base 2? If I redefine R and C to work with base 2 numbers, would this structure work with base 2? It will work with any base, because that's how we do base 10. I mean, this is how we do multi-digit addition, regardless of the base. Now, when you're learning multi-digit addition in third grade or second grade, how come your teacher did not express multi-digit addition this way? I have no idea why. This is so much more clear than the way they do it in classroom.
Well, because if we add start and grade numbers, it probably wouldn't work as well.
Yep. Well, because this involves a lot of abstraction. Okay, and a third grader cannot handle abstraction like you can, because you have learned a lot of other things over time, so you have the ability to handle the abstraction. But the power of the abstraction is it allows you to start with something that you're familiar with, extract the structure out of it, and then reapply that to something that is new, base 2. Well, let's check out base 2 then. Okay, I'm going to use an example on the whiteboard again. So let's check out the base 2 number addition, 1011 plus 0112. Okay, that's what we are dealing with. So once again, this is X, this is Y, but this time I want to I want to express the K and the Q as well as the S. Okay, so this way everything is expressed. So this row here, can people in the back still see this, or should I move it up? You still okay? Okay. So this row is going to be the Q in the notes where I have highlighted. This is going to be the K, which is the carry, and then the last one is going to be the sum. Okay? So we look at this and go like, oh, what about K0? K0 is here. It is the carry for column 0. It is by definition 0 because we don't have any less significant digits. So put a 0 here according to that definition. Okay? So we look at Qi, Q of I, so I'm just pointing out here. So Q of I is the result of adding the digit x of I and y of I. I can go from 0 to whatever number you want. So in this case, we're just dealing with 1 plus 0. What is the R or the result of 1 plus 0? 1, okay, so 1 here. Now we have to look at 1 plus 0 because that would be the sum, because the sum S of I is taking Q of I and K of I and look at the result of adding these two digits. So we are looking at adding, in this case, the 1 and the 0, which turns out to be just a 1, okay? Is that okay? What about K1? K1 is K, I plus 1 here. I is 0. So 0 plus 1 is 1. So K1 is the carry of adding x0, y0. Do they have a carry? 1 plus 0 does not have a carry. What about the other addition? What about adding Q of 0 to K of 0? Q of 0 is 1, K of 0 is 0. So we are looking at the carry of 1 plus 0. Does that have a carry? So neither has a carry. 0 plus 0 is 0. So K1 is a 0. Okay? Now we look at this one here. We look at Q1. Q1, when I is 1, then Qi or Q1 is the result of adding x1, y1. x1 is 1, y1 is 1. 1 plus 1 has a result of 0. Okay? We'll worry about the carry later. Well, I guess since it's the next item, let's do it. So when I is 1, K2, because 1 plus 1 is 2, is the carry of adding xi, yi plus something. Well, the carry of adding x1, y1 is already given us a carry of 1. Okay. Now we want to look at S1. S1 is here. When I is 1, then we can calculate S1. S1 is the result of adding Q1 and K1. Q1 is a 0. K1 is a 0. So the result of adding 0, 0 is also a 0. Is that okay? Because this is spelling out all the individual terms that is already in the notes. Is that okay? Cool? All right. So now we have 0 plus 1. I'm just going to shortcut now, going a little bit faster. 0 plus 1 is a 1, has no carry on its own. But 1 plus 1 has a 0 with a carry. 1 plus 0 is a 1, has no carry on its own. 1 plus 1 is a 0. Huh?
1 0.
1 plus 1 is a 0 with a carry.
Yeah.
Yep, but that's it. This one has no place to go. It is not a part of the sum. Because when you're talking about fixed width addition, whatever width you're dealing with, in this case 4 bits, dictates both the numbers that are incoming as well as the number as the result. So the result of adding 1 0 1 1 and 0 1 1 0 is actually 0 0 0 1. But we have an extra carry that is stored here. So the extra carry is actually stored by the processor for something else. We might need it later. So it is actually remembered. After an addition, the processor can remember, oh, the result need one more digit than we actually had. It actually would remember that. Yep.
What happens to the value when it gets stored?
It gets stored in a special place. Okay. Yep.
So I mean, just to like illustrate that, so like, like I had a handful of stones, and then there were a couple other stones that like, I didn't have room for, but like I still had, put it on the table. grab the ones on the table, because those go with them?
Sort of like that. It's kind of like your basket can only hold so many stones, right?
Yeah.
So you have, you bring along, okay, so in this case, we are talking about, this is 11, and this is 6.
Mm-hmm.
But your basket can only hold up to 15 stones.
Yeah.
Okay, so when you add 11 to 6, what do you get? You get 17, right? So when you get 17, but your basket can only hold, no, that's not right. 6 plus 11 is 17, so 17 is right. Okay, so that's fine. So your basket can only hold 15 stones, 0 to 15 stones. So when you go to the market and you bring along 11 stones and somebody else gave you 6 more stones, then you go like, oh, my basket is full, I cannot carry 17 stones home. So what you do is to say, okay, I'm going to carry 1 stone, but I have this other thing that's going to remember that, oh, there are 16 stones that you owe me, that belongs to me, but I cannot carry it in my basket. Yep.
Which flag does the computer set? Is that the carry flag?
It's the carry flag. Yep.
Okay.
Yep. Question? Same question?
But
There was
just
another
make it
hand.
sound like more like we keep the carry and then leave everything else.
Well, there's still the basket, which is the sum.
Yeah.
Then there's still a basket, but you have one extra thing that can help you remember that, to say that, well, in addition to what I have in the basket,
Oh, yeah, makes sense.
okay, is that cool?
Yeah.
Okay, yep.
So in a specific digit sum, we could actually end up with less.
With less?
Yes.
Less in the
Because-
basket.
Less in
But
the
there's one that extra thing that says, oh, if this thing is 1, it means, in addition to what I have in the basket, I would have, in this case, 16 of those stones. Yep.
It's like an IOU note.
Yes, kind of like an
In the
IOU.
basketball, throw the IOU note 15 and the 1 stone that I can carry.
Exactly.
And then
Well,
I can
the
turn it
IOU
back.
is not going to be in the basket because your basket can only carry stones, but the IOU is in your pocket. Yeah. So is that cool so far or not?
So what is
No.
is the basket the amount of data allocated in this example?
Well, the basket has to do with using 4 bits, using 4 zeros and ones.
Okay.
What is the range of quantities that you can represent? 0, 0, 0, 0 is a 0, 0, 0, 0, 1 is a 1, and then 1, 1, 1, 1 is the best you can do. That's the maximum you can represent.
Got
And
it.
that turns out to be 15. So that means with 4 bits, you can only contain 0 to 15 stones in the basket. You don't have space for 16 stones.
We're going down the wire.
Hmm?
We're going down the wire since this is connected to hardware.
Yes.
Since you've got, what is it, pin size for your bus?
Oh, you mean the width of the bus?
Yeah.
Yeah. So, but it boils down to the same concept. It's your, if your basket can only hold, if you have 4 bits, then your basket only has a capacity up to 15 items. So if the sum is exceeding what you can represent in the basket, you have the extra IOU note to indicate that in addition to what I have in the basket, if this thing is a 1, it means that I have another 16. I possess another 16. Is that okay?
No, yeah. That
Okay.
answers my question.
Okay, cool.
But
Go
how
ahead.
do we show that mathematically in the equation?
Mathematically? Oh, it's easy. See, so in this case, we say k bracket. Okay. By the way, what is this one? If I need to use that notation, this is going to be k bracket what? 4. So we say k bracket 4 is a 1. But there's no s bracket 4. S bracket 3 is the last one. But you have a k bracket 4 that will still be remembered by the processor for further calculation purposes.
Right. So we have 1011 plus 0110.
Mm-hmm.
That equals 0001.
With a carry of 1.
So after the 0001, we put k bracket 4.
You just say that there's an overall carry of 1.
So I'm saying like, would it be like 0, 0, 0, 1, and then R1, 0.1?
No, oh, you mean the notation? No, you can just spell it out. You just say that with a carry of 1. Yep. So there's an overall carry of 1 after the addition. Is that okay? All right. So what we'll do in the lab is kind of a continuation of this notes, because I can't really give you anything to do in the lab until we get to the point where we can say, oh, we can draw circuits to do it. Okay, so that's what I will do is I will draw circuits to do this stuff here, and I will implement a simple carry ripple adder that can actually do addition. So that's what I'm going to do in the lab, and you're strongly recommended to be there, because you want to learn how to use the tool in Logisim as much as possible.